In this week's lecture videos, or the series of lectures that we will follow, our main focus will be on buckling analysis. Now, buckling is a common problem that is dealt with by aerospace engineers because of all the thin-walled structures that are dealt with in aerospace engineering applications. Apart from the standard thin-walled shells, most common buckling problem with respect to column buckling of beams is already quite a classical problem that will be known by most of you who are not involved in a lot of buckling analysis of thin shells or composite plates or laminates, etc. In general, buckling does not always have to be a non-linear problem. Under certain circumstances, such as pronounced rotations before reaching a limit point in buckling, the structure may require to be analyzed with non-linear effects. So, as part of this lecture series, I will first start by defining what is buckling, giving you the importance of something called stress stiffening or the geometric stiffness matrix that we have discussed before in buckling analysis. We will look at a standard buckling problem by means of terminology as what it means to be at a limit point, at a critical point, etc. We will go through a simple energy-based illustration of the column buckling problem and move on further towards calculation of buckling loads and where exactly does the nonlinear buckling analysis arise. In order to describe a simple or a common buckling problem in terms of the paths that are taken by the analysis, I would like to bring your attention to a buckling problem of a simple beam which is subjected to axial load P in a compressive manner as shown here in the figure. Under this compressive load, the beam is expected to bend with a displacement VC, let's say, at the midpoint. All the definition of the beam, of course, is always important to have. However, that's not the point of interest here. The idea is that under a certain load, axial load P, the beam will behave in a certain way prior to buckling. So if I plot here a load displacement curve, which will be P versus VC, then we would see that the load increasing from 0 to P is basically a primary path which is the original load displacement line or the load displacement curve. Now at a certain point, say somewhere over here, there is a critical load PC which is reached at. At this point, there is a secondary path or an alternative path that originates, and this is called the secondary path. The two paths will intersect at a point which is called the bifurcation point, which refers exactly to the point where the PC is reached. Past the bifurcation point, the primary path is going to be unstable, although mathematically it's possible to compute. However, a real structure will follow the secondary path instead. Now in this figure, you see the secondary path to be a horizontal line because in this example problem, which is shown here with the column, we assume that there is very small displacement that is made. However, it doesn't have to be horizontal. It can also be increasing upwards or reducing downwards depending on the condition. Of course, there is also another kind of buckling problem which you have already faced before, and that was to do with the shallow truss that we looked at. So we can always have a certain condition where your structure behaves like this, where you have a point where you reach your maximum load and then the behavior changes, and this point is called the limit point. This is common to see in a snap-through buckling problem. There is another term which is also used for a critical load, which is a collapse load. A collapse load is a maximum load a structure can sustain without going through any further gross deformation. So in common usage, a critical load may refer to the bifurcation load, a limit point load, or even a collapse load. Mathematically, bifurcation buckling can be described in a different way. As you can see in this problem, there is a certain load P at which suddenly the behavior of the structure will change. So at this load P, you can either be on the primary path or be on the secondary path. So you can exist in both situations, which is what is referred to in the case of bifurcation buckling. So bifurcation buckling mathematically can be described, or physically can be described, to occur when a member or a structure converts the membrane strain energy, so this is of course related to the in-plane conditions, to the bending strain energy, which goes into bending or out of plane behavior, with no change in external load applied. So if you consider thin plates or thin shells, then the membrane stiffness is much greater than the bending stiffness. So large amount of membrane stiffness is membrane strain energy is stored within the structure without causing very large deformations. But at some point when it is large enough, the load is large enough, or it comes to that particular point where the membrane strain energy is transformed into the bending strain energy, then that is a point where you would see buckling to occur, or this kind of instability in the equilibrium configuration will arise. Now, in finite element analysis, the effect of the membrane stresses on the lateral deflection of a structure are accounted for by means of a certain matrix that has already been introduced to you in the previous week. This particular matrix is called the geometric stiffness matrix. It is also sometimes referred to as stress stiffening matrix. In the previous videos, it was referred to as matrix Kg. This is a function of the element's geometry, displacement field, and a state of membrane stress. Because it is independent of the material properties, it is also applicable despite any anisotropy and yielding that may occur in the problem. As you may recall, the Kg for a bar element that we studied was a function of P by L times a matrix depending upon the degrees of freedom that were part of this matrix, and so on. So you see here it would only depend upon the geometry of the structure and nothing to do with the material.